So hello everyone, my name is Ahmed. I am a Galaxy developer and I am a member of the Schatz lab at the Johns Hopkins University. And this year, I will be presenting some of the improvements made to workflows and their user experience in Galaxy. So I'm sure most of us here must be aware of what workflows are in Galaxy, but for those who aren't, they are an integral feature in Galaxy. And really, the best way to get the most out of Galaxy as a user is to chain the large amount of tools available on a given Galaxy server into these reproducible, shareable, and scalable pipelines called workflows. Now, the typical workflow journey in Galaxy for a user goes something like this. You can create a workflow or edit an existing one in the all-powerful, ever-improving workflow editor. You don't need to start from scratch necessarily. You can find an ideal workflow for your analysis in the list of workflows in a server, or as we found in this conference, that there are external sites that have really nice peer-reviewed workflows as well. And then naturally, once you've found the ideal workflow, you provide the required inputs and then run it. And then you can observe the results in our recent introduced last year, the invocation view, which shows you real time the workflow updating and everything. So while there have been many cool improvements to each one of these components, for this presentation, I will focus in on the workflow run form, which has seen a lot of enhancements in this latest release. So, I mean, we always share improvements for the UI that we make all the time, but this, in particular for this feature, the philosophy that we worked with was that we realized that it would be cool to provide the users a unified single interface experience for running workflows in Galaxy. So the user should be able to stay on the run form itself and set up an entire analysis from beginning to end, ready to run. And we'll see how we did that. So here's an example of what the workflow run form looked like in the past. Now, with the history and activity bar in context and the user being aware of how to bring data into Galaxy and make it meaningful for a workflow, this makes quite a lot of sense. It's like any other form that you fill out. But then we'll realize there's some detours and some things that you need to know firsthand before you can run. So for example, bringing data into Galaxy. So for an upload, uploads in Galaxy are global. Now, global here means that the uploaded data is not necessarily tied to that specific workflow that you're looking at. The data simply goes to your history. And from there on, it's on the user to find the appropriate files for the specific workflow that they're running, because there could be unrelated data from separate workflow runs in the history, right? So what that means is that they need to understand how the history system works, the way it was introduced. The reason it's called history instead of a file explorer is because it's like a history of your entire analysis. It's not just a place where the uploads live, but it's a history of multiple analyses. And if a user doesn't know that, they run 2, 3 workflows, stuff can get confusing in the mix. And then an additional concern is that workflows require dataset collections, which are very cool. And that's another thing that the user needs to be aware of. So to explain very quickly, collections are really the best way to organize data. In Galaxy, you can group multiple files together into specific structures required by inputs and workflows and tools. A common example of this, which I'm sure several of us will be aware of, are forward and reverse reads. So once you've uploaded both of those files, an input for a workflow might require a collection of exactly that structure. And so you can place that into something in Galaxy, which is called a paired collection, which is just one of the many types of collections you can make, which has a forward and reverse dataset. And then the example that we've shown here is a list of paired datasets, which is a parent collection which has multiple of those forward and reverse reads in child collections. More on this in the next presentation, courtesy John Chilton, who's done some amazing changes for collections recently. And so the idea is that in order to run workflows, especially for new users, they don't need to only understand what a collection is, but also find out how to make one in Galaxy. And so the existing process for this, which is slightly changed, you select the files that you want to make the collection out of, find the collection builder, and then make that collection, right? But again, like I've shown here, you're clicking on those different options, and the new user doesn't know what a list of lists of dataset pairs means, right? Because there's so many structures you can have. So they need to be aware of all of these things as well. Now, this is not to say that users have never been able to navigate any of these steps and never run workflows. I'd also like to give a quick shout out to the GTN, the Galaxy Training Network, which is a great resource for learning all of these things. But we realized that what if we centralize all of these steps in one place by integrating all of these processes directly into the workflow run form? Then we can remove all of these detours and let the workflow itself take the center stage for the analysis. So to do a contrast and compare, this is what the existing interface looked like, and here's what we've sort of changed it to. Now you'll notice that I've collapsed the history, which you can obviously bring back, and the side panels now work a lot better in Galaxies, that they're only there when you need them. But the idea is that you shouldn't be needing those anymore. You should be able to do the entire analysis within one pane, ideally, center panel. So again, if we take it step by step, instead of readying your input data in separate parts of the interface, we've integrated the uploader and collection creation into the run form. So for example, for dataset inputs, where the input is in the collection, you just click on the upload button, and the familiar Galaxy uploader pops up. And obviously, once the file uploads and materializes, a minor detail which is useful is that it's actually set as the current value, so the user doesn't need to look around the history and find that data set, and it's just going to be set right there and then you can move on to the next input and so on, so forth. Another detail is that the data type is also, it filters the list of data types to the ones provided by the workflow author for each input there. So that's cool to have. And then again, for collections, you have the same idea. Instead of having to create the collection separately, you can now create it directly in the form. So this video shows that you click the create button, and again, the uploader pops up. You do an upload like we've always done in Galaxy. For example, here we have URL data upload. And once that data is ready, so now this specific input required a list of dataset pairs, again, a parent list with forward and reverse reads. And that's what we made here. So the form detected that instead of throwing all the builders and you having to choose, it's going to detect the type of structure that is expected. And so once we click create, it'll make it. And another minor detail is that now we also see the actual current value of whatever the input is in the workflow. It's good to have. Instead of finding it in the history, you can just, in fact, even get a peek at the data if you'd like in the run form. So to summarize, what this means for users is that they can now upload data and create structured inputs and prepare everything in one place, resulting in a truly unified and simplified setup experience. Some other changes that I'd also describe are a minor detail. We've improved the header at the very top, which has more information about the workflow, such as information about the author and whatnot. The workflow run settings menu has also seen improvements. We feel like some of these options weren't as prominent before, which they are now. It's like it persists across sessions. And for example, that second option right there, which we made it work with the job cache. So that's a really cool option that we now, we're shouting that this exists. Please use these options. So that's good. And you can now see, we also saw this yesterday, where you can see the README in the run form, which is, you can have nice markdown documentation, which a lot of times DocStore, you would import a workflow, it would have that documentation outside of Galaxy, but it wouldn't come in. So now we have that too. This is something I enjoyed working on, which is the workflow run graph. Your workflow will often go beyond the first 1 or 2 or 3 input steps. So it's cool to see all of the steps in the workflow in the editor instead of just seeing a bland form with just 3, input fields. So that's good to have too. And a final feature which we cannot ignore is the fact that you can now rerun workflows using the same exact input data as before. So for example, here we had these 3 parameters for a former run. And so once we click rerun, it's gonna, because we want to use the exact same data sets, it's gonna sync the history up so that we have that history enabled. And then, it's the same exact inputs as before. And so in that sense, you're rerunning that workflow. It lets you know if you change the input from the original run. And essentially, once you click run, it's going to be your typical workflow run. All right, for a detailed description of not just these workflow improvements, but everything that we do in Galaxy all the time, please check out the release notes. That's the documentation website. It has all release notes from the past 2. And thank you very much. Thank you.
Okay. Okay, so I'm going to highlight some actual use cases derived from the IWC that we've seen over and over again. We've seen this website, and there's this sort of anti-pattern that's prevalent currently. So if I do a search for RNA-seq quant, I'm going to get 2 copies of the same workflow, essentially. The only difference is that one handles single-end reads and one handles paired-end reads. This is a big maintenance overhead, and it's kind of confusing to users. We want to get away from them having to know about these details or worry about these details. So in Galaxy 25.0, we've got a new collection type and a new way to do workflow inputs. You can sort of now say that this workflow consumes a list of either paired inputs or unpaired inputs. And that's really, there's like a mountain of work underneath here, but it's really quite easy to grasp what's happening. Now you can do either. And so for the methods developers, for the people writing the workflows, all you need to do is swap the input and then either update your tools, or you can use all the existing tools in the workflow in the same format, but you just do a split step at the beginning and sort of take parallel data tracks and then do a merge. Everything we've added to Galaxy in recent years around conditionals, et cetera, makes this, it should make this super simple. For the pipeline executors, I'm going to show some of this off. It's easier than ever to build collections in Galaxy. So if I select some data sets, I don't even need to know if it's paired or I don't. When you go to the collection builders now, these current options are simply the ones we saw from the older screenshots just in the last slide. You can say auto build list, and it's going to look at the data and it's going to say these are paired data sets. So it's going to bring up the paired collection builder with everything auto paired. And it should handle most cases. You can go in and tweak it, and you can figure things out, but it's easier than ever to sort of say, I've got some data, and I'm going to send it to this workflow. You also have a bunch of advanced collection options, and I'm going to talk about these, but they are advanced things. They're sort of niche. And one thing is to build these this new structured like lists of paired or unpaired. So while that workflow can take just a normal list of pairs or a normal flat list of samples, you can also build sort of a mixed combination using this collection builder. I think it's kind of niche, but it's available. You should know about it, but probably you won't need to use it day to day. Anyway, that's the first use case. The second use case that I'm going to talk a lot about is Wolfgang's chip-seq workflow. But this is a common paradigm. As these IWC workflows become more production ready and more sophisticated, the structures you have to supply to the workflows are becoming likewise more complicated. So this workflow was going to require the researcher to upload a sample sheet, which is basically this table I've highlighted here, which captures a bunch of information about how the samples relate to each other. So we've got like something that's sort of effectively a Galaxy list identifier. We've got a treatment condition, replicates, and then what the control is, if there is a control. And the tough thing here in Galaxy, if you try to map these structures to sort of traditional Galaxy dataset collections, is that control feature. Without that, really what we're looking at is two different dataset collections. A collection that's just a list of pairs. That's the top one here is the controls, and then a nested list of pairs where you've got multiple layers of lists, and then you've got pairs at the deepest layer. And so I hope this visualization makes some sense, but for the treatments, you've got what the treatment is and what the replicate number is. And these are all things that Galaxy has been able to represent for 10 years. But we really haven't had a nice UI for constructing this kind of thing until 25.0. And so in 25.0, again, we have these advanced list creators, and one of them is nested list of pairs. I can now build that thing right inside of Galaxy. In the past, you would need to use something called the rule builder, which I'll bring up over and over again. But the rule builder is great, but it's a sort of programming DSL thing, and it's complicated to learn. It's powerful and good to learn, I think, but we want to be able to do more without that, I think. So I can build up this list builder, and I now have a graphical way to build that data structure for those controls, the simplified versions of those controls. I just specify the treatment and the replicate number, everything's still paired. So this new paradigm for how we build collections in Galaxy can support building these more sophisticated collections. And that's great. There are some limitations to this approach. Maybe you're already tracking your data in spreadsheets, maybe you're downloading tables of URLs from public websites, and maybe you feel just more comfortable with data entry in your favorite spreadsheet program. So maybe you have data that looks like this, or links to data that look like this. And maybe you want to build your collections outside of Galaxy. This is something you'll be able to do in Galaxy 25.01 or 25.1. So I mentioned the rule builder. Part of in Galaxy 25.0, we've rebuilt it to be a wizard. So it's a lot more helpful. I encourage you to check it out, but this talk isn't about that. But at any point in this wizard, you can sort of say, I've got this spreadsheet that has headers that Galaxy should be able to interpret what they mean, and I should be able to build the collection right from that. And so you can either just drop your spreadsheet right in there or click upload, and Galaxy will do all the work of sort of looking at the headers and so on and saying, well, this is a URL, this goes here, this is a second URL, it goes here. These are what the list identifiers mean, et cetera. And so from that spreadsheet, I can infer that this is a nested list of pairs, and you can just upload them right to Galaxy this way. All you need to do is drop that spreadsheet in and give it a name. So if the rule builder was a visual programming language for data import manipulation, these fetch workbooks are magic. So you don't have to learn that. And they work for a lot of very simple use cases and relatively complex use cases also. And any workbook will do, any sort of tabular file, you can drop anything in there. But if you're going through the rule builder and you're going through the wizard, you can sort of say, I want to build this kind of collection, and you can download a nice template. This template's not essential, but it's got some nice bells and whistles. So if you have this template in Galaxy, it comes with help for what the columns mean. It comes with validation, cell validation, make sure it's a URI, make sure et cetera. So you could get a nice template. Then you've got a second tab in the workbook that specifies any sort of extra metadata you want to specify, whether it be hashes or tags or file types or genomes, et cetera. Anything you would specify with the rule builder or advanced upload options, you can specify right in the workbook. And that's all documented. And so that's for sort of simple list, like nested collections. But coming back to this use case, we still have these controls, right? This use case is not captured by collections as we've thought about them for 10 years in Galaxy. So we still need this sample sheet, this table to be uploaded so that we can map things out correctly. I'm going to argue that this is kind of a crummy user experience to upload this table. But before I do that, I'm going to sort of say it is the state of the art. I think that PR could be merged and it would be fine because it is basically what you would do in NF Core or Nextflow. It's, Bioconductor is amazing and has all sorts of like amazing ways to set up data and stuff. But if you're going to work with tables, it's still pretty similar. Gotcha. Thanks. 2 minutes. But these are sophisticated use cases. There's a lot of problems. How do I validate that sample sheet, et cetera? Anyway, we get that the UX is not great there for either uploading or running, for defining the workflow or for running it. But sample sheet collections are great because they let the author of the workflow specify what these sample sheets should look like and present a nice user interface for filling it out. This uses Ahmed's great work for sort of, okay, if I specify a sample sheet input, I have different ways to do it. I can paste in a bunch of URLs, and I get a nice spreadsheet version. It's automatically paired all the data. It's got the columns that can be filled in. All the validation happens. If there are drop-downs, this is all typed, et cetera, et cetera. You can do it with external workbooks also. Same thing. You can download any sort of workbook can do, but you can download a special template for your workflow. Yeah. Anyway, I ran out of time. I knew I was going to run out of time. I'm going to post the slides in Slack somewhere. I've got actually double the number of slides. There's a ton, but I didn't want to. I thank Ahmed for. None of this would be possible without being able to specify the inputs for the workflow inside the workflow run form. And then thanks to Marius, Wolfgang, and Bjoern for working through these examples with me, and the whole IWC and GTN for building amazing things with Galaxy workflows and collections. Thank you.
Fantastic. Thank you so much. So I'm presenting this talk on behalf today of Junhao Chu, who did all this work. And what I want to talk to you about today is a data analysis agent inside Galaxy. And so as we kind of learned yesterday, oops, that's the video automatically is playing. Let me try to go back because I want to pause it. Oh, okay, we'll just let it go for now. So the data analysis agent that we're going to talk about today is an interactive tool inside Galaxy that allows you to analyze your data sets using natural language. So we're using large language models here. The idea is that you ask the agent for an analysis, and then what happens is the agent goes, plans what to do, writes the code, executes it, potentially corrects any errors that are associated with it, finally returns the results. So what you're seeing here is scrolling down through an exploratory data analysis. So the original query was, can you run a data analysis for this tabular data set? And so far, we've mostly focused on tabular data sets. Now, the reason that we chose to kind of perform this experiment to say, what could you do in a very simple way with Galaxy and large language models is because Galaxy has traditionally had this gap in the past of being able to manipulate data well. So generating simple plots, removing certain columns, building correlation heat matrices, all of these are possible in Galaxy, but running their own tools is somewhat cumbersome. And so an agent kind of bridges this. It meets the accessibility goals of Galaxy because you're writing in free text, but it's very flexible at the same time, which is not something that we've traditionally been able to do with Galaxy. Importantly, with this tool, you can take the plots that you've generated and the tables that you've generated with the agent and move them back into Galaxy for downstream analyses. So it really is nicely integrated into Galaxy. So I want to take these next 3 slides and kind of walk you through the 3 different versions of the agent that we made and share some lessons learned, more or less, as we've experimented with this new technology. So the first version that we made of this agent, we used something called the Pandas AI library. It was very particular to working with tabular data sets. It didn't do a lot of thinking. It executed basically one request at a time, but it allowed us kind of this foothold to say, we can create these conversations with our data. The agent will support these conversations. So perform this analysis or remove this column, for instance, and then I want to take the subsequent table and plot it, for instance. So you could take this 2-step process. We integrated many different large language models, so it's not just one model in particular that we're talking about, but several different models. And we did integrate it into Galaxy, so you could move in and out of this agent and use it with other Galaxy tools. Before I forget, there is this highlight here about how much everything is costing, because it's important to keep cost in mind. We're an open source community. There are different options we can use. In this case, we're using a ChatGPT model, and this relatively complex query that I'll explain in more detail as I go on cost us about 4 cents. Okay, so version 1. Version 2, we kind of stepped it up and we said, well, we really want something slightly more agentic that did more complex reasoning. And so there's this concept out there called reasoning and acting, or REACT, that we incorporated into version 2. This allowed for more complex analyses. So it wasn't a one and done analysis. It was perform something and maybe the agent could reason through multiple steps. Doesn't always work well, but it worked better than what we had before. We also extended this beyond tabular data sets. So this agent now has the capabilities not only with tabular data sets, but FASTQ files and so on. We added a notion of suggestions. And suggestions really are pretty important here, because when you think about what large language models are potentially good at, part of it is being creative. And helping you be creative as a data analyst is saying, what's next? And so the agent had these suggestions that we built into version 2 that says, okay, based on what you've done already, here's what you might want to do next. And we added some user interface features such as bookmarking. Version 3. So version 3, I think, is our most recent incarnation of how this all looks. And I would say this is both an advance in terms of how we use these artificial intelligence models, but also how we think about the user interface. So trying to go beyond chat was something we really wanted to think about in this version 3. What you can see here is that the analyses, the results of the analyses are showing up on the right, but the text, your conversation with the agent, is showing up on the left. That's deliberate at this point to separate out these two things, because most of those products that you see on your right are the stuff that you want to come back to and work with. And trying to put them into a chat where you're going back and forth saying, well, I'm talking here, I'm producing a plot here. What if I produce 3 or 4 plots? How do I interleave that into the chat? Was just not clean. And you see this kind of style of interaction where, to some degree, the agent is starting to generate some user interface components and help you build a user interface on the fly, so to speak, is something that I think will be more common as we move on with agents in general. From a technical standpoint, we started using this library called DSPy. And we did this because trying to optimize the prompts for what we wanted to do was not working especially well. And DSPy provides some ways to do automated prompt optimization. I'll talk a little bit more about that in the subsequent slides. As a result of optimizing our prompts, though, and kind of splitting things out, we get faster response time as well. So you can see that it actually runs pretty quickly, still at a pretty low cost. Okay, so some technical details about prompt optimization, data, and flow code. These are some common questions that we get, so I wanted to share it with this audience. So prompt optimization starts with the prompt that we write ourselves, but what we do is we give it some best examples. So in this case, we have a 9-example data set, not a big data set that we come up with, but we give that to the library and it optimizes a prompt on our behalf based on those inputs and outputs. It can do this for any model that you're using, whether it's ChatGPT in the case of a commercial model or something like DeepSeek or Llama 4 if you're using an open source model. That's kind of abstracted away from you, and you can work at this higher level and say, here's the task that I want to do. I want to ask a question, and what I want to do is get a response back, sometimes plots, almost always code, and I want to get an explanation of why you chose to do what you did, so kind of a chain of thought. And we're able to do this with our prompt optimization work. In terms of data and code flow, the agent sends only a small snippet of data up to the model. And this is important for bandwidth reasons, for reasons in terms of token usage and cost. But what the agent does effectively says, I have a data set on disk in this case. I have a preview of the data set, which is kind of the schema in particular of the data, as well as the first couple of columns. And from that, that's enough actually most of the time to generate really good responses. The code comes back from the large language model and it is executed locally in an isolated container. So if that code goes bad for some reason, it is fully isolated. In terms of how we think about this last version of the model, because we're a machine learning lab, by and large at this point, we wanted to make sure that it was good at machine learning analyses. And we have managed to get really good results at this point from this agent by asking it to do different types of machine learning with different types of auto machine learning language libraries, such as AutoGluon. And the cost is still pretty reasonable. We're at 5 cents for this particular query to run this machine learning analysis. From a UI perspective, these suggestions are still embedded in the interface, and bookmarking is possible as well, so being able to come back to it. Kind of going beyond the chat interface is one of the really important things that we're trying to push on as we experiment with these agents. Galaxy, of course, is focused on the user interface in many respects. The previous talks, the talks throughout this conference really emphasize that it's important to say, what does this user interface do and how can we make it useful for the scientists that are out there? And so suggestions and bookmarks are one way that we can get at this. When we talk about agents, reproducibility and robustness come up a lot because these agents don't always give you the same answer. But as you hopefully are starting to see, we are not just using large language models, we're coupling them with other aspects of software libraries and user interfaces to help us get to our ultimate goals. And so in the case of reproducibility and robustness, we do save the code that the large language model generates for complete reproducibility, if that's what you want. But when we think about this from a scientific standpoint, there's kind of been this discussion over the last couple of years about reproducibility versus robustness when it comes to, 1 minute, thanks, when it comes to data analyses. So reproducibility is precise reproducibility when it comes to a particular data set and a particular analysis. Robustness is this concept that you could maybe use different methods on the same type of data and get similar results. Robustness may be our goal in the long term as scientists because we don't want to necessarily be dependent on any one method. And what large language models allow us to do in a lot of ways is to test those concepts of robustness because by default, everything is stochastic, which means you're not always going to get the same exact analyses that come out. And so in some sense, what we're aiming for with this agent is robustness rather than precise reproducibility, although we enable both right now. So quickly to wrap up in 10 seconds, as we think about where this agent goes in the future, it goes in several logical directions. Multiple data sets rather than a single data set, additional data types, especially single cell and imaging are high on the list, deeper integration with the Galaxy UI in a lot of ways. Somebody finally got to that notion, or got to the alarm. Okay, so thank you so much to my lab and to Junhao who did all this work.
Sounds good. Everyone, my name is Bryan Raubenolt. I'm a postdoctoral research fellow in the Blankenberg lab at the Center for Computational Life Sciences at the Cleveland Clinic. And today I want to talk to you folks a little bit about quantum computing and what we're trying to do with it going forward in and out of Galaxy. So quantum computing is it's really an entirely new way of thinking, and by extension, an entirely new way of computing. So as opposed to classical computing and traditional von Neumann architectures where, bits are explicitly either 0 or 1. In quantum computing, the basic unit of information is the quantum bit or qubit, in which you have, if you think of it as a sphere over here, in the North Pole, you have the 0 state, and the South Pole, you have the 1 state, but much like different points on a map on a globe, you could have different states of the qubit, right? And this actually allows these qubits to exist in states of superposition, right? So not explicitly the 0 or 1, but some sort of mixture of in between. And then on the other hand, quantum circuits, as opposed to your traditional logical circuits, in this case is a basic unit of computation, and it's a set of quantum gate operations on these qubits. And what they can do is they can create the superposition states of these qubits, and they can entangle them. Now together, superposition and entanglement, what that does is it essentially gives you an ability to simultaneously compute or sample in a way that we haven't been able to do so with computers before, at least on a single computer chip. So with that in mind, what can that sort of computing power give you? And there's different applications and optimization in other areas, but of course, machine learning is one of them. So fundamentally, quantum machine learning and classical machine learning are very much the same in the sense that you start from the same point, right? You have your data set and you have a certain amount of features, and then you give it that some algorithm, it recognizes certain patterns, and then you get a prediction or label, right? A classification at the end of it. Now, the main difference is over here, where, when you're doing quantum machine learning, you're going to take your raw data and then you're going to encode it into quantum states. And after you do that, you give it to a quantum machine learning algorithm. And then you have a readout of your circuit, which gives you what we call expectation values of your circuit. And from there, that's transformed into the prediction or label. So there's a couple extra moving parts here, but there are some potential advantages, right? And some of them include an exponential increase in processing power, again, by way of superposition and entanglement. There's also the possibility that you can recognize more complex patterns in your data, just because once you transform them into quantum states in the Hilbert space, there are things you can pick up on that you can't really see in a context of classical information. Kind of like a Fourier transform, right? When you transform things into the space of frequency domain, there are things you can pick up that you can't in the traditional time domain. There's other areas where there could be advantage, enhancing optimization in classical machine learning alone. So if you just use it to optimize your classical machine learning algorithm, there's a possibility that it could be more generalizable, meaning that you could create more robust models with less training data. And a couple possible advantages, the ability to deal better with imbalanced data sets, as well as just natively being able to handle periodic data sets better. And that makes sense, right? Because this is all based on quantum mechanics, and quantum mechanics is the language of waves, right? So, periodic data is definitely an area where these algorithms do pretty well, and it's something we've seen in our work so far. So with that in mind, of course, where can you actually apply this stuff? Well, we can think of in the context of omics and beyond, or healthcare and life sciences. And most of you are bioinformaticians in this room, so you're familiar with these data sets in which you're handling information on genomics, transcriptomics, metabolomics, epigenetics. And from there, you basically, again, you transform your data using a feature map, you fan it off to some sort of parameterized quantum circuit. In this case, it's known as an ansatz. And then you measure the outcome, right, after you run the circuit many, many different times. And when you translate that information back to the classical domain, there's different benefits from it. You could use it for patient stratification, prognosis, treatment selection, as well as biomarker identification. Okay, and so let's talk about the code, right? So I spent a good bit of time over the last year developing a code base with some collaborators at IBM to essentially automate both classical and quantum machine learning. If you guys want to check it out, this GitHub for the source code's right there. But these are basically the primary modules, right? So over here on the left, we have the data set selection, right? So this is where you can create your data, or you can upload your own data. We have the model runners, and then we have the performance evaluator, and lastly, the automatic model selector. But at the end of it, essentially what you're going to get is a data complexity evaluation, which I'll get to in a bit, the performance of your models, which you can measure with an F1 score, accuracy, AUC. And then once you have these two, you can start to see correlations that you can then train an oracle with. And that's what we did. So QSage is our oracle that recognizes these complexity evaluations with model performance. And I'll explain to you how that works here in a bit. So what do I mean by data complexity? So any given data set, you can measure certain characteristics about it, right? And we're trying to answer, what is it about the data? When is quantum machine learning useful? Or more broadly, like when your data looks a certain way, what machine learning algorithm is best suited for it? And you can look at things, for example, like kurtosis, right? How peaked or how tailed your data is. By that meaning how much of your data distribution is centered around the mean versus around the outliers. If you think of a manifold complexity and intrinsic dimension, so if you have a data set with many, many different features and you reduce that down to its principal features, and let's just say they're in a three-dimensional space, what does that manifold look like? Is it rugged? Is it rough? Is it flat? You can also look at things like Fisher discrimination ratio, which is a measure of the variance between classes or the variance within classes. This is how you measure imbalance in a data set. But you could also look at more conventional things like skewness, right? Like, is your data skewed to the left? Is it skewed to the right? Is it skewed around the middle? Is it evenly distributed? These are some of the things that the data complexity evaluator is actually calculating on the fly for every data set that you give the code base. So the way it works, the whole pipeline is you have a main function, we call it the profiler, and the entire thing is run by a single config file. So one of the things that we want to do is just make this as turnkey as possible, so you don't have to dig into the source code hardly at all. So you select all your parameters, your input data sets, the models you want to run, how many iterations of the optimizations you want to run, and so on and so forth. And after that, of course, your data set is chosen, and then you immediately run the data complexity evaluation. From there, you do any possible dimensionality reduction, right? So if you have 100 features in your data set and you want to speed things up, you can reduce it down to, let's just say, the 10 most principal features. And then from there, you run the data complexity evaluation again on the now embedded data, right? And then all in one slingshot maneuver, you run 6 classical machine learning models, 4 quantum machine learning models. And then from there, you can analyze this data, right? You analyze the correlations between model performance and data complexity. And those correlations we feed into our Oracle QSage, right? And essentially, it's giving users the ability to, essentially, without running the entire pipeline, to look at the data and just go, hey, we think you could probably use quantum machine learning. If so, use this method, or use only classical machine learning. So a priori, it can give you some insight. And so far, we trained this on over 200,000 experiments at this point. So just a quick recap of the analysis that's kind of automated as well, right? So in this case over here, you have your standard bar plots and box and whisker plots that give you an idea of the performance of all 10 machine learning models across your data, which basically helps answer how do the methods perform with your data and which method is the best. And then the other part of the automated analysis is these hierarchical clustering heat maps. I'm pretty sure many of you do this in your normal bioinformatics work, in which, in this case, the complexity measures, which is about roughly 15 of them. So you can see over here on the right, they're normalized between 0 and 1, and then the Euclidean distance is used for clustering. So you end up with similar intensities for complexity measures for similar data sets, which is what you see over here. These two are the most similar. This starts to become an outlier, and the last one of the longest branch is the outlier. So now this helps us answer, is there some structure or pattern in my data? Now you have performance, you have your structure and complexity of your data together, you can get correlations. And these are Spearman correlation plots in which you can see that for all these data sets and for these complexity measures, you can your data sets are either anti-correlated or positively correlated with a particular complexity measure. And what this helps us do is not only analyze, again, like what ML method is best suited for our data, but it also helps us identify a switch possibly, right? When you go from classical machine learning to quantum machine learning, which is what we see over here. For the same exact data that we have here, we see a completely different set of correlations between all the quantum machine learning methods and all the classical machine learning methods, both in the nature of the correlation, positive versus anti-correlated, as well as the magnitude of the impact on the F1 score. So the Galaxy tool that I'm developing to go along with this, I'm trying to keep it as simple as possible. I want it to be as automated as the original source code, right? So a user just has to, there's 2 inputs, a config file, and then the data set you want to feed it in the form of a data frame that's, classically labeled. And the config file can either be uploaded or sort of, developed on the fly. Okay, so wrapping it up here. Of course, everything has its limitations, right? So currently, unfortunately, quantum machine learning is limited to supervised learning with only binary classification. That's because when you measure the circuit at the end of it, your qubits collapse to either 0 or 1. Dimensionality reduction is almost always required just because the way it works out, when you transform your data, every feature in your data set corresponds to 1 qubit in your circuit. And quantum computers are still in the early stages. We don't have thousands of qubits yet. On average, it's much longer runtimes than classical machine learning. QML might still have a long way to go, but the promise is still there. We're starting to see certain data sets and regimes where it's actually outperforming classical machine learning. Future work, we're going to do some extensive testing on biological data and continuing to train the QSage, and we're holding a tutorial at ISMB next month in Liverpool. But this is the first step in helping us find out, and hopefully the bioinformatics community can help us find out when is quantum machine learning useful. And with that, all this happened because I got a chance to work with some really cool people at the Cleveland Clinic and IBM. And also thanks Galaxy for providing the scholarship that gave me a chance to come here and present this stuff to you folks.
Hello, everyone. My name is Jamie Park. I'm a PhD student from Michigan, Van Andel Institute, and I mainly work on aging. I feel a little out in the sense that everybody's doing cool like Galaxy workflows, but today I'll demonstrate on how we can use the torch for the R package to generate deep learned epigenetic clocks. So to explain a little bit about what epigenetic clocks are, I have to explain a little bit about the DNA methylation. So DNA methylation, as its name suggests, are these small modifications on cytosines in a CG context in the genome. And they have a lot of major functions, including like cellular differentiation and function as well. So it's very important to maintain a stable and consistent methylome. But unfortunately, when we're we're supposed to have like this very clean compartmentalized methylome where you have these repeats that are farly methylated to suppress like ancient viruses. But on CpG islands, which are basically these promoter sites for genes, you want these to be very, very clean. When you're born, these are relatively pretty clean, well compartmentalized. But as we age, there's an erosion of this methylation pattern. And in the epigenome, some parts that didn't have methylation start to gain methylation, and some parts that are supposed to be methylated lose the methylation. And researchers have been interested in identifying these specific sites and the trends of this aging pattern. And about 10 years ago, Steve Horvath, a bioinformatician, who was trying to look at the blood samples from homosexual individuals, realized that they can't really predict homosexuality from the methylation of homosexuals, but they can predict age. So using a machine learning algorithm, he generated what's known as an epigenetic clock that can relatively predict the chronological age from blood samples. So it's been 10 years or almost like 12 years since the first release of the epigenetic clocks, and many new updates have been released. These are the big three epigenetic clocks. The first version, as you can see, the mean absolute error for the age was around 7 years, but the second version, which was released around 2018, had like 3.1. The Hannum clock and PhenoAge clock tried to challenge the Horvath clock, but it's still around like 5 years of mean absolute error. Recently, because there was such an emerging literature for epigenetic clocks, there was been a review published, and for the chronological age, you can see that most of them are actually programmed in R, and they use this method called elastic net. And some of the machine learning scientists would probably already know what this is, but it's basically ridge plus lasso. These are regularization methods to improve the prediction for this algorithm. And because usually there's way more probes, in this case, Illumina epic arrays, which has 850K probes, then we have samples. Fitting a line when you have more parameters than samples, the size doesn't really work. So you add a penalization to each parameter. So that's the ridge and the lambda and the lasso. And they usually use the package GLMnet to make this methylation clock. And elastic is great, but it does have some limits. One is that they assume that the biological aging pattern for the methylation is linear, and usually it's not that simple, right? Usually we go through this nonlinear trajectory like as we age. And another part is that it completely ignores the interaction between CpG sites because the genome is not really like a very straight string. It's more of a tangled string because it has all the 3D conformations. And also because we feed the lasso, the multicollinearity just basically chooses a random probe when you have more than a few similarly behaving tropes. So due to this, they've had like recently a lot of people have been trying to have like deep learned epigenetic clocks. To just give you a few examples, this is from the Sing lab where they used a pan tissue methylation pan-tissue array to feed in and train a deep learning epigenetic clock. This one's from a different lab that used a little bit of an XAI component to their epigenetic clocks. And most of these pipelines utilize either PyTorch or TensorFlow. And I was wondering if R, having its ability to utilize GPU nodes, is capable of training a epigenetic clock. Using Torch, it has a R interface to PyTorch, basically. And I'm just citing a few codes from the script that I've uploaded on my GitHub repo. I mainly followed a lot of the great tutorials from Sigrid Kedana that has a really great tutorials on how to use the Torch for R. So it's a relatively simple design where you just have a 3-layer multi-layer perceptron architecture with GPUs that is not that great. That is not like amazing. And the training hyperparameters, I just kept it relatively simple. And what you're doing is simply just trying to predict age, just a single variable, single numerical variable by feeding a bunch of epic arrays. To give you explain a little bit about the training data itself, this was a curated data set from the Biomarkers of Aging Challenge. So it basically has a bunch of epic array, the microarray data with methylation data, and has some metadata, including its age, sex, and whether it's disease or not. And this was already curated from the Biomarkers of Aging platform that you can access through a Python library. You can see that just looking at the age distribution, most of them are 0 because there are a lot of babies or umbilical blood cord samples. And most of the tissue frequency comes from blood because blood is just very easy to get. So if you feed all of this data, I'll explain a little bit about the training loop. First, you have to load and initialize the data set. I realized that you do need to have a relatively lightweight format like a feather arrow or NPY. And I'm trying to record the time point to see if there's any better things I can do to optimize the parameter. For this training, I just gave it a pretty standard, like a 70% to 15-15 data split. I have to scale the feature because the beta values need a little bit of standardization. And then I create the tensor, which is basically converting the error matrix into a tensor. And then I'll go through just, the code. You can more details on the GitHub, which I will show you the QR code at the last step. But you can actually train the model. You go through the training phase and the validation phase, and then I just choose the best model and test it, and then I save it. And surprisingly, I was surprised to learn that it actually performs decently well. The mean absolute error for the neural network trained clock was 2.25 years, which basically beats all of the current elastic net-based models. So that is very, very interesting. So to give a summary, RTorch can be a very powerful tool for deep learning. And these deep learned epigenetic clocks can predict age far more accurately than the current generation of most elastic network clocks. Just to give an acknowledgement, I really thank you so much for Peter for allowing me to come here. And thank you for Nathan for curating the data set. And special thanks to Zach and Kin for really helping me out to set up the CUDA on our studio. It's not an easy task. If you're interested more about the script itself, this is my GitHub. Thank you so much.
Thank you. So our lab is developing this second generation of machine learning tools. And it's not only the tools, but also a concept that we are trying to embed inside these tools. And this is because science has embedded machine learning, analytical and predictive AIs into it. So people are using a lot of these techniques now. And recently, Nature just published a paper showing the top most cited works on the 21st century. And no surprise, 4 of them are directly related to machine learning. Therefore, we want to respond to that with a concept first before we build our tools. And that's when GLIM shows up. GLIM stands for Galaxy Learning and Modeling. That it has a really straight vision. We want to have accessibility in our tools and best practice because this is really important for science, reproducibility and scalability as well. So the technical overview to GLIM is we are going to ship 3 main tools into Galaxy Toolbox. And we abstract the names to make the tools related more to the concept than the tool itself. So the names of the tools are the data set they're going to be trained on. So it's called a tabular learner, image learner, and multimodal learner. Here on your right, you're seeing some supporting tools because we figured out that some researchers work with the digital pathology and they need some pre-processing on their data sets for the image before they can input them to GLIM in our tools. So that's why we have also shipped these supporting tools along with the GLIM. So now that I show you the concept and the tools, I want to show you underneath the hood what is happening. So we select the libraries based on those concepts. So we are looking for libraries that has best practice embedded, comprehensive, that we can leverage different analysis in them, and also AutoML that takes from the user the burden to select too many options and make more accessible. So for the tabular learner, we have PyCaret. There are several points that I could point as a good selection, but I'm gonna just mention the top ones. So for PyCaret, we have a rapid experimentation. When you run a PyCaret experiment, you can run more than 10 models at once and pick the one that was trained the best for your data set. For the image learner, we have Ludwig. It has a great modularity and flexibility to have different encoders and decoders and also change model architecture. So this was a great pick. And for multimodal learner, we have AutoGluon running because it has a native multimodal data support. So we're expecting with multimodal learner that the user are coming with 3 main data sets: text, tabular, and image. So they can congregate all those 3 data sets and run an experiment. So just to give you an example how this is going to shift the experiments for machine learning, here I'm bringing one paper that was published in 2024 in Nature Cancer. As you can expect, there is a GitHub repository filled with different files and different lines of code to train different models so they can compare the results. But if you apply GLIM, then this becomes 6 steps to run the same experiment. So you need the inputs for your data set, select the target column, the model task, if it's classification or regression, select the models if you want to select, it's up to you. So if you don't select any model, it's going to run all the possible models, and that's it. You're set to go and run your tool. And as I said, we want to have best practice, and GLIM has this amazing report that we are trying to make concise and also informative for the user. So eliminate that black box from machine learning. So for image learner, we have reports for category and binary composed by 4 tables that you can see the metrics, compare them, also hyperparameters, and 90 figures with graphs showing the performance, the model, the training, and also the validation. Same thing for the tabular learner, 4 tables that you can see them and compare your model. And because best practice, we are trying our best to have them embedded in the tools, but we also need the user to be aware how to use those metrics and results. And that's why we are also paying attention to that, putting a guideline to the user right in front of them so they can click and see what those metrics means, because sometimes you can forget those, and also make recommendations for when to use, if you have an imbalanced data set, which metrics you should use. Here I'm bringing some examples of those tools working. So we take one paper that was published using skin lesions from a public data set, and we train our model. So as Dr. Goecks was mentioning, we are looking for robustness, not reproducibility. So we are just throwing the data set and waiting for the results from the model that we have in the tool. So as you can see here, the accuracy, precision, recall, and F1 score, they look pretty much similar that the ones that were published in this paper, showing that our tools are robust, doing their jobs itself. Also, sorry, this is, okay. So the next one is for the tabular learner. We have patient response for the immunotherapy. This is the paper that I showed you previously. And we did the same thing. Take the inputs that they use and run through our tools to see the results. And as you can see, the table right here showing that we are outperforming the accuracy, but the rest, the AUC and precision recall curve, it's also similar, showing that our tools are robust. So to summarize, our tools are 3 integrated learners that encapsulate end-to-end machine learning workflows through intuitive interfaces. We try to abstract case steps such as model selection, and it's important to mention that we are abstracting that, but if you're an experienced user, there is a button that you can also select those informations if you are comfortable to do that. And lastly, use cases demonstrate that it's robust and probably is going to help have good results being presented in the papers. For future work, as you can spot, we are just finished the multimodal learner, so it's about to come. And we want to have a publication with that. And we are also thinking about the step of the pre-processing that we are not touching with this work, but we also need to think about that to make sure that what it's put in our tools is a quality tool, quality data set. And also improve the AutoML because there is a lot of things that we can be aware. For example, data leakage is one of those things that we face sometimes, and we want our tools to be able to work with that. So, of course, this work was only able because we have a great team with Dr. Goecks in the lab. So thank you so much. And
hi, everyone. I'm Greg Watson from Oak Ridge National Lab. I want to talk to you a little bit about what we're trying to do and hopefully get people interested in maybe collaborating or at least trying out some of the tools and software that we're building. Stands by itself. Just going to continue on. So at Oak Ridge, we have a couple of different facilities and lots of instruments. So these are neutron facilities. We have a spallation neutron source, which has a linear accelerator, a ring to collect the protons, and then a target, and then that goes off and hits a bunch of different instruments that are spread around it. We also have a nuclear reactor, which produces a steady stream of neutrons, which has also a whole lot of different instruments associated with it. The thing about these particular facilities is they collect the data by bombarding a sample with these neutrons, collect the data. That data needs to be cleaned up, and that process of cleaning up the data is called reduction, which doesn't actually necessarily reduce the amount of data or reduce the size of it, but removes all the instrument artifacts and so forth. Once the data is reduced, only then can you analyze it. So you can't analyze the data before it has been cleaned up. The analysis aspect requires visualization, and usually it's running some kind of simulation alongside the experimental data and then comparing visually the results of the two to see whether they coincide some way. So there's just a couple of examples of analysis that have been undertaken. So the thing is that every one of those instruments needs a different tool to do the reduction. And each one of the techniques also requires a different set of analysis tools. And so there's a lot. And we wanted to use Galaxy to run some of the reduction workflows and maybe some of the data analysis workflows. And I did not touch that at all. That's pretty, is there a ghost in here or something? But anyway, there's just a lot of tools to port to Galaxy. And then a lot of these, the analysis tools have user interfaces themselves and they need interaction and so forth. So we're trying to figure out, okay, how can we leverage Galaxy, but also, try and cope with the tool set that we need to deal with. So obviously Galaxy can handle workflows. We have implemented a lot of workflows for the neutrons people. But the bottom line is that they really want to have a different user interface, a different way of interacting with their tools than using the Galaxy user interface. So this talk really is about, okay, is it possible to use and leverage all the Galaxy functionality, but provide a different way, a different mechanism for being able to do that. Obviously the limitations on the Galaxy user interface, the fixed nature of the layout and so forth. The tools interfaces are very simplistic, although, we've seen some advances in that, which is great to see, but nevertheless, they don't really approach the kind of user interfaces that we want to be able to deal with. And then the visualizations, even though there's some really cool visualization tools that are available, they tend to be post-workflow or, post-analysis kinds of visualizations, whereas we want to be able to do the visualizations as part of the workflow or even before the workflow is executed. So we created this thing called the Neutrons Open Visualization and Analysis Framework. And essentially it boils down to a way of building single page web applications that interact with Galaxy. So we've got a simplified way of building these web applications, but we leverage the Galaxy infrastructure to do all the deployment, to run the tools, to provide the user interfaces for the users, and then they can also leverage all the capabilities of Galaxy at the same time. So I know that sounds like a lot, and I'll try and explain that in the 5 minutes I've got left. So obviously you've got pulsars, we have Galaxy, so that's taken for granted that we need that functionality. We also use containers extensively, so we containerize everything. It just makes life a lot easier. It's not absolutely essential, but it certainly helps us in terms of deployment especially. So the main parts of this framework are some Python libraries that we call, so they're all prefixed by Nova, but there's Nova Galaxy, which is essentially a high-level version of BioBlend. So it gives you a higher-level interface to BioBlend, so you don't really need to know the low-level intimate details of the Galaxy infrastructure and APIs and so forth. So people can develop it at that higher level. There's a user interface library, which we're calling Nova Tram. That's a French word. That's why it's not train. And that provides a way of interacting and building user interfaces, and I'll talk about that more in a minute. And then we have another library called Nova MVVM, which provides some functionality for building these single-page web applications using the model view model architecture, or design pattern is really what it is. We use Copier to allow users to take a template version of this application and then add their own functionality to it. So Copier is a really cool tool if you haven't heard about it, but it gives people a good starting point for building their applications, so they're not building them from scratch. And then we also heavily utilize automated containerization and automation tools and so forth. Again, not part of Nova, but we utilize it. And then we have a dashboard that gives people a way of getting into this whole environment without having to go through the Galaxy user interface. What do these applications look like? Well, they consist of a view model, and a model. And copier is the thing that instantiates this for you. The model is the UI independent part. It's where you put all your data. The UI is obviously the thing that you see in the web page and so forth. And then the view model is essentially a piece that converts the model data into a format that the view can present to you. And the MVVM library that I mentioned before is the glue that binds the data between the model and the view. And this all happens with no code. You write a couple of lines of code and it automatically keeps the view and the model in sync for you. The TRAM library that I mentioned is the thing that provides the interface to the visualization aspect of it. So we have integration with Matplotlib, with VTK, both client and server-side rendering. We have PyVista integration as well for doing visualization. And then the Nova Galaxy library is the one down here, and that allows these applications to interact with Galaxy, run workflows, get data, and all that kind of stuff. So the key features to this are pure Python code, the data binding, which provides the automatic update of the model and the view. We use Pydantic for doing data validation in the user interface, and we support other frameworks such as Bootstrap, Panel, and PyQt. So just a few examples. I'm just going to skip over these ones because these are some legacy codes. This is, it's really quite hard to see on here, but this is a user interface for just entering data. This is a more sophisticated user interface that integrates some visualization, 2D visualization tools such as Matplotlib with the application. We have a 3D visualization tool that has X, Y, and Z slices, and this is all done. This particular data set is about 20 gigabytes, and you can render that in the web page. And then this is an example of a user interface that has a 3D model of a crystal, that has a 2D slice of that crystal, and then it has some 1D plots or 2D plots, I guess, of some of the properties of the crystal. So all these, you can see it kind of, I guess, gives you a feel for the types of applications that we want to be able to do, and then have these applications interact with the Galaxy framework. So if you want more information, it's all open source. There's a GitHub repo, there's documentation on this. The template application you can download from our GitLab repo at Oak Ridge National Lab. And there's also a tutorial. If you're interested in going through the tutorial, it can show you how to develop these applications. And we would love to have more people contributing to this. If you're interested, please contact me or open an issue on the GitHub page if you'd like. So thank you.
All right. Hello, everyone. My name is Fabio Bombo. I'm a postdoctoral researcher at the Center for Computational Life Sciences of the Cleveland Clinic, the Blankenberg Lab. And today I'm presenting our first effort toward the automatic integration of tools in Galaxy. We are going to focus on the Anvio suite and an AI-driven automation pipeline. What is Galaxy? I'm not sure I really have to answer this question here. I think it's pretty clear what Galaxy is at this point. But really in brief, so Galaxy is a web platform that powers open, reproducible research by making it accessible for everyone, regardless of their computational programming and coding skills. So as Galaxy grows, we see a bottleneck emerging here, which regards the integration of new tools. Especially those highly modular or complex toolkits. So, in this talk, I'll show how we tackle this challenge specifically for the Anvio suite and how we experimented with a state-of-the-art language model to further reduce the manual effort in integrating tools into the platform. So Galaxy is built upon three guideline principles: the accessibility, so making it easier for researchers to run complex analysis, regardless of their coding skills; reproducibility, so capturing every parameters and making analysis fully reproducible; and transparency, so allowing users to share and publish their data, workflows, visualizations. So while these benefits have brought Galaxy where it is today, integrating new tools, especially those highly modular, complex suite of tools, still remain quite challenging. Each tool must be wrapped in XML, so inputs must be defined with precision, command lines and logic must be as well captured, output files must be clearly described and annotated. So this approach works very well for small tools. It doesn't scale very well when we are dealing with toolkits with hundreds of CLI tools, for example, making manual wrapping quite impractical. Manual wrapping is highly flexible, but it comes at a cost. Each tool has to be wrapped in XML, an XML file which describes the inputs, the outputs, the execution logic. Complex tools have interdependent options, so making manual work very prone to errors. And again, in case of a very large suite of tools, this quickly becomes a bottleneck. So let's talk about Anvio. This is a powerful, popular Python-based toolkit for metagenomics, pangenomics, genomics in general. It's very popular, and we think that the whole Galaxy community will really benefit from its integration into the platform. And there is only one problem here, which is it contains over 100 tools and subcommands. So these numbers make the manual wrapping quite, of all these tools quite impractical. At the same time, it makes it, an ideal test case for what we would like to do. So trying to integrate all these tools into the Galaxy platform in an automatic way. Our approach. We developed the pipeline here. The execution logic is actually pretty easy. We iterate over the Anvio Python scripts, and so note that Anvio relies on the argument parse module to handle input arguments and parameters. So what we do here is overriding the call to the argument parser with a custom class that we called fake arg here, and that we made up as an extension of argument parser. So at this point, when we execute a specific Anvio tool, it's going to initialize a fake arg object that gives us full control over these tools, arguments, parameters, parameter names, types, and most importantly, their metavar information. And we actually use this metavar information to decide whether a specific input argument refers to a number or a Boolean true-false flag or an input file. Like in this example, if a specific input argument is supposed to refer to a file, that must be translated into a specific XML block in the final wrapper for Galaxy. So with this approach, we can now capture the structure of every Anvio tool directly from its source code. And here is a very short video that shows all these 100+ tools integrated into the Galaxy platform, into a local Galaxy instance. So our pipeline works specifically for Anvio at this point, but we are working on its generalization that would allow to at least work with, on every other Python tools that rely on the argument parser module. All right, so I said that I was also going to mention something about the automatic integration of Galaxy tools via AI. So here it is. We experimented using DeepSeek R1. It's an open source large language model that we try to train using Galaxy wrappers. And of course, our goal here is to try to explain what kind of wrapper we wanted to generate in a natural language way. So with the hope that it could, speed out a working tool ready to be integrated into the Galaxy platform. Why DeepSeek-R1? It's an open source model. Its performances are very competitive if you compare it with other closed source models, like ChatGPT, for example. And it also supports 4-bit quantization, which means that you will potentially end up with a lightweight model that could eventually run and fine-tune on consumer-grade hardware. So here is the idea. This is how we trained our model. We have a prompt template with some very basic and standard instructions, like you should act as a developer of the Galaxy team. Your job is integrating tools into the Galaxy platform. So when prompted, generate the XML wrapper for the following tool. And here is where we should add as many details as possible about the tools we want it to generate wrappers for. This is a very basic example about an Hello World tool. It just prints Hello World to the standard output, followed by a custom message. So we are telling it how this CLI tool is supposed to be run, specifically all its input arguments, just a custom message in this case. And at this point, our model is going to generate what is called the chain of thought, which is a particular type of reasoning that should terminate with an answer. That is, in our case, the XML code that defines the Galaxy wrapper for the Hello World tool. So following this logic, we took all the over 500 high-quality wrappers from the Galaxy IUC, the Intergalactic Utilities Commission, and we started parsing their shed YAML files. So we are interested in particular in the homepage URL tag or whatever other kind of information that could explicitly or implicitly provide us with as many information about these tools as possible. So in this case, we are searching for the homepage URL so that we could follow that link with the hypothesis that it is going to land us on a web page with a description of the tools and potentially containing information about its input arguments and parameters. So we parse those pages and we use their content as the tool description. And now we want to train this model, so we also have to provide the expected output, which is the actual XML code. And we repeated this process for all these 500 plus tools in Galaxy IUC. All right, this is our very first attempt at integrating Galaxy tools into the Galaxy platform using AI. This is a very far from being a perfectly functional approach. However, it can still be used to drastically reduce some manual effort. So with that said, we are still facing with a lot of challenges here. First of all, again, the generated wrappers are not likely to be fully functional at first and still require some manual refinement. But more importantly, we're still trying to figure out how to automatically test the generated wrappers. And this is a problem that affects also the automatic integration of the Envio suite as well. With that said, our future is very clear now, extending the training of the DeepSeek model with tools from the Galaxy toolshed will definitely improve the model's capability in generating these well-structured and functional wrappers. And also providing more precise and detailed information about the tools will definitely be beneficial. It will for sure perform much better than simply copy-pasting the content of a web page. And I'm going to conclude. And so yeah, and also the design of a strategy for automatically testing the generated tools is definitely going to be crucial here. And I think that's all. Thanks a lot for your attention, and thanks for the Galaxy organizers for awarding me with the scholarship this year.
Yeah, so basically, we wanted to improve the job scheduling in Galaxy with something we've called TPV Broker. So this work is part of a EOSC project, European project, which is called Euroscience Gateway. The idea behind it is that we could leverage like the distributed compute infrastructure in different European partners. Yeah, these are the institutes involved, each having their own dedicated infrastructure.
different types of clusters. So what we wanted to do was to be able to distribute analysis, so Galaxy tools across all of these institutes. So to do that, each of the institutes kind of set up their own pulsar endpoint, and all of these pulsar endpoints were all kind of registered in Use Galaxy EU, and are all usable and accessible from there. So that's something we call the pulsar network, and of course there's pulsars in Australia as well, and of course in the US as well. But that aside, so now how do we efficiently schedule jobs from a Galaxy server to this network? So firstly, the default way of doing this in Galaxy is through TPV. So TPV has knowledge of all the registered compute endpoints, and it has the relevant job metadata. And so TPV is actually responsible for matching a job's specifications, as job requirements, to the available resources or the available compute endpoints, and kind of figuring out which of the compute endpoints is most suitable. And that's kind of the basic purpose of TPV. So this is kind of what it will evaluate. So it evaluates tool specifications, but it can also look at specific details about a user. So for example, a different user might have different requirements. For example, for a training, for example, you could imagine a user needing more resources. There's also a Galaxy role, so that could again be a training role, for example. But it combines all of these requirements for a job and evaluates that against the available destinations. So a basic example of TPV, so you have there, bow tie in this case with the required cores and memory, and then it'll try to pick the best, actually not the best, but the one of the suitable destinations. In this case, there's only one suitable destination, since we need that amount of memory and cores, and the other Condor destination, for example, wouldn't be able to fit the job. More detailed example, because you can do additional things. You can tag both tools and destinations with specific tags, which makes it a bit more dynamic. So you could have a destination that only accepts high memory or prefers high memory jobs. But you can also tag, for example, the destination as offline. So even if it is the better destination, it wouldn't be able to accept it because it's marked as offline. And you can go even further with rank functions. So rank functions are kind of basically, it allows you to actually insert any kind of Python script to come up with a ranked list of destinations. So this is just anything that you want to do in Python to sort the available destinations that TPV knows of. You can do that here. And this is actually our entry point for our TPV broker. So the default way of working in TPV has limitations due to TPV not being aware of the load on the different compute endpoints. And that can cause some destinations to not be used at all, and some that might have a high load, but TPV isn't aware that there's a lot of jobs running there, or a lot of jobs in the queue. So that causes significant delays for the jobs to finish. Also, it's not aware of where exactly your compute endpoint is located. So some jobs might take a long time just because the data has to transfer for a long time. So what we came up with is, like I said, the broker. So basically, it's an API. It's a Python application that calculates the most optimal location or compute endpoint based on real-time metrics we collect of each of these endpoints. How many jobs are running, how many are in the queue, and other similar metrics. So with all of this information that we collect about the destinations, we can start to make better decisions. And technically, it also makes use of a RabbitMQ queue to transport these metrics between the destinations and the TPV broker. Lastly, there's also a visualization tool we've developed for this. So this is kind of an overview of what this looks like. So from a user perspective, they would just submit their jobs through use Galaxy EU, and TPV plus the broker would then just decide what is the best location for it to run. But here just the important part is that we collect all the information in the central location, and it's TPV that through this API endpoint can collect the necessary or the ranked list of destinations. So we came up with a quite simple matchmaking algorithm as well. So there are several things we had to consider about the destinations. So definitely exclude the ones that cannot meet the requirements of the job. We also wanted to figure out which are the closest compute destinations, and then we calculate a matching score of the available destinations. So this matching score, basically we want to account for the queue size. So this is the queue matching factor, which is the median queue time times the queue size. And then the compute matching factor, which is the same for the running jobs, or so and then we just combine them really easily. And that kind of is our total matching score of destination to specific job. So this is the visualization tool we came up with called the Galaxy Job Radar. So this visualizes jobs across all our available endpoints. And it could help admins figure out or at least be aware of which destinations aren't currently operating correctly, for example. There's a QR code for it, but this is kind of what it looks like. So you kind of see the job distribution from Use Galaxy EU in this case. So the benefits are basically that it handles real-time resource tracking, and so therefore it improves the resource utilization. It's more scalable if you have a large number of compute endpoints. And it also handles compute endpoints being down, because we do check if our Pulsar nodes are actually operational. Let's see. So future work, we want to apply, or actually improve our algorithm by not just having a strict comparison between resources needed and resources available, but more of a kind of a binned approach, saying that kind of a fuzzy way of matching destinations to jobs, and not a strict yes or no. We want to improve the energy, or we want to actually include like energy usage or efficiency, or as a sorry. I guess I can leave it at that. Just thanks to all the people involved, and that's it.
Okay, hello, my name is Marius. I've just started the final year of my PhD at the Open University in the UK, where I've been using Galaxy to reanalyze public data. So today I'll kind of talk about how I've been using it to analyze this big combined data set that contains over 1 million individual heart cells. So one of the reasons why I created this data set was because an aim of my PhD was to kind of see how much we could actually do with the single cell tools on Galaxy. So my supervisor said, go and make a big data set. I don't think they were necessarily expecting it to be quite this big, but Galaxy has kind of proven pretty effective at analyzing it so far. Using Galaxy has kind of been a key part of my PhD. It's kind of one of the kind of aims that I had at the beginning was to see what I could do on Galaxy. All of the analyses that I'll show you today were performed on the EU Galaxy server. So that was a big benefit for me because I don't think I would have been able to analyze such a big data set given the computing resources that were available from my university, which was effectively just a laptop. So having access to this free server was kind of essential for this analysis. I did have to ask them for increased storage because this is a very big data set and it only gets bigger than what you analyze it. But I did find that Galaxy was very useful for working with it, partly because of all the stuff that we've been talking about today, like the workflows and the data collections. I can set stuff running on a Friday evening and I can come back on Monday morning and hopefully see sort of loads of green completed steps in my Galaxy history without having to sit there with my computer open while I'm working on it. I also found that Galaxy was really useful for organizing my data. So I particularly liked kind of having these tags for naming my data sets. And I kind of had a very structured naming system for all of my histories of the different versions of the analysis. Another kind of key part of my PhD is working with public data, because this is this massive resource that's out there, but kind of its value is really in its use rather than its just existence. So there's lots of different reasons why you might want to use public data. In the case of this particular analysis, what I was really interested in was getting hold of more samples and more cells, particularly the cardiomyocytes that I was most interested in, and also being able to make new comparisons, because there's a very limited range of data sets from human hearts, because it's quite difficult to get hold of samples. So sometimes they're quite limited in what they're looking at. They might only have healthy cells or only have diseased cells. So by combining these data sets together, I'd be able to make new comparisons. There were two kind of main issues with this approach. The first of all was getting these data sets to work together. So in terms of just like the data format, that was a problem sometimes, but there are kind of tools on Galaxy that can convert your data formats. So that didn't turn out to be as big of an issue as just getting the metadata organized, because different scientists will give you different names for their metadata. They'll provide it in different ways. Sometimes you have to comb through the publications in order to find the information you needed. So that did take quite a lot of time and wasn't always something that was easy to do on Galaxy. The other issue was kind of handling the batch effects between these different data sets. And I was a bit dubious as to how well this would work on Galaxy, but actually for this data set, the Harmony tool on Galaxy has actually been able to do that pretty effectively. So what was I actually looking at? I was interested in what was happening in the heart in a condition called atrial fibrillation, which is the most common form of arrhythmia. So it's an irregular heart rhythm and it's been implicated in up to 1 in 5 strokes. So it does have potentially serious consequences. And the cardiomyocytes, or the heart muscle cells, play a key role in it. So in the healthy heart, you have specialized cardiomyocytes in the conduction system that produce these electrical signals. They send them out and they tell the other cardiomyocytes when to contract. In atrial fibrillation, you still have those normal signals, but you have other cells that in other parts of the heart, more cardiomyocytes, that start producing their own electrical signals, causing other cells to contract at different times. And that's why you get this irregular heartbeat. So, if we want to kind of look at these cardiomyocytes specifically, the specific cell type and what's changing, single cell approaches would seem to be really useful, but there are kind of problems with getting cardiomyocytes with these techniques. They can be too big and fragile to capture with single cell experiments, and they can also get filtered out a lot of the time when people are analyzing single cell data, because they have a lot of mitochondria because they need a lot of energy, and that tends to be taken as a sign of poor quality cells traditionally in a single cell analysis. Whereas if you're setting that threshold too low, you're actually getting rid of some of your good quality energetic cells. So one way around this is to perform single nuclei sequencing, where you just collect the RNAs that were present within the nuclei rather than the whole cell. But obviously you're only getting like a smaller population of the RNAs that are present. So you're not necessarily getting the full picture of what's going on with your disease. So we decided to try a different approach to see if we could get more single cell cardiomyocytes by combining multiple data sets. So you can see there's loads of different data sets here. Some of them only have healthy cells, some of them only have disease cells. Each of them has their own kind of smaller population, particularly for the single cell analyses of cardiomyocytes, but by combining them together, we should be able to get a big population of these cells to analyze. So I gathered together these 7 studies. Some of them were single cells, some of them were single nuclear. They covered 10 different regions of the healthy adult heart. I also included one fetal data set, because one of the effects associated with atrial fibrillation is dedifferentiation of the cardiomyocytes. And I also included some samples from people with heart failure as well as atrial fibrillation, so I could compare those diseases. So I ran this big combined data set through the ScanPy clustering pipeline using Harmony for the batch correction. And I ended up with this UMAP, which is just showing here. Each dot here is one of those individual cells or nuclei. They've been coloured in based on the cluster they were assigned to, which is effectively a group of cells that had similar RNAs in them. And they matched up very well with the different cell types that we know to be present in the heart. The ones we're really interested in are these two here. The green cluster is the ventricular cardiomyocytes, so from the 2 bottom chambers of the heart. The orange cluster are the atrial cardiomyocytes from the 2 top chambers of the heart. But I didn't just want to look at the cardiomyocytes. I wanted to know what were the differences within this group, particularly between the healthy and the diseased cells. So I picked out these cardiomyocyte clusters and I ran them through the ScanPy clustering pipeline again. I did this in various different ways, which is why I've got so many different histories for this analysis in my Galaxy account. The one that I'll talk to you about today is where I filtered these cardiomyocyte clusters to just include the single cell data, because one of the aims here was to see if we could get a bigger population of single cell cardiomyocytes to look at. So when I did that, I ended up with these 4 clusters, and we could, based on these, we could see that, and based on where each of these samples was taken from and the genes that were being expressed here, I was able to identify that there was a cluster of healthy atrial cardiomyocytes and one of healthy ventricular cardiomyocytes. There was a cluster that had a mix of healthy cells and cells from people with heart failure, but the one that I was really interested in was this blue cluster, which was mostly made up of cardiomyocytes from people with atrial fibrillation. So I wanted to know what was making these cells different, and what that could tell us about how these cells might be changing in this disease. So still on Galaxy, I looked at the differentially expressed genes in this cluster. We could see that among kind of the top ones for that blue cluster were genes like TMS-B10 and TMS-B4X, I believe, which are kind of potential signs of this dedifferentiation that we might see in atrial fibrillation. And I then looked at the biological processes, the Go terms that were associated with these differentially expressed genes. We could see some related to proliferation and the cell cycle, which again could be signs of dedifferentiation. Some responses to muscle stretch, which is one of the mechanical effects of atrial fibrillation. But a lot of these terms were related to regulation and communication with the immune system. So I also performed a pseudobulk analysis, again, still on Galaxy. You can see here on the left-hand side, the differently expressed genes between the samples in the healthy atrial and ventricular clusters. And as expected, these are genes that are known to be expressed in those regions of the heart. And then on the right-hand side, you can see that there were a load of genes that were kind of more expressed in the atrial fibrillation cluster, that weird blue cluster, than in kind of the healthy atrial cells. I was comparing them to the atrial cluster because they were mostly atrial samples in the atrial fibrillation cluster. So these genes are kind of not necessarily genes that you would expect to see much of in cardiomyocytes, but when we look in the literature, we can see that in certain circumstances, when there's inflammation going on in the heart, you do see these genes. So that's kind of another effect of atrial fibrillation that has been suggested to happen. So this does kind of back up the idea that these are cells that are changing or affected by atrial fibrillation. The next thing I want to do with them is to do a cell communication analysis, which we can't currently do within Galaxy, but it is on the kind of list of tools that the single cell and spatial omics community wants to add. So hopefully I'll be able to do that on Galaxy soon. But I think I'm still kind of investigating this cluster, but I think it does kind of prove that we can take these two public resources, the publicly available data and the publicly available Galaxy server, and we're actually able to kind of find out new things about what's happening in disease just by following analyses that are in our Galaxy training network tutorials. So I think I'm slightly over time, but I'd like to say I do have a poster later, and to thank my supervisors at the Open University and the British Society for Cell Biology for funding some of my travel costs to attend this conference. Thank you.
So good afternoon. Today I'm going to introduce you Gentomics, our bioconductor package for multiomics data integration and visualization. Well, first of all, let's start with the reason behind the development of this package. As you know, in the last year, we had an explosion of omics data availability. We have genomics data, transcriptomics, epigenomics, and so on. So different tools came out for the analysis of this data, but actually most of these tools are for dimensionality reduction, sample clustering, or to stratify samples in some way. And what is missing is tools that are able to integrate at gene level the different omics, also to understand the impact and the interplay between the different omics and their impact on gene expression. So to solve this need, we developed Gentomics that integrates different omics and is also able to detect the interplay between the different omics to understand how, for example, copy number or other alterations can impact gene expression, and also to support the biological interpretation of the results of our models. So these are the basic features of our package, where first of all, we give the user the possibility to integrate, for example, genomics alterations such as copy number variations or methylation with gene expression data, and also to integrate other regulators such as transcription, the information about the correlation between the expression of transcription factors or microRNA with target gene expression. And finally, also provide the so-called multiomics integration, where all the previous integration are performed together. And the last, but one of the most important part of the package is the visualization of the results. In fact, we provide a comprehensive Shiny app to dig inside the results of our models. The core statistical model that we use are two. We have the linear regression model for microarray, or let's say all data, and then the negative binomial model for RNA-seq data. This is just a scheme to highlight how complex is the package actually. In the actual number of functions are more than 150, but we have just 18 functions that are exported for the user. And we provide both two omics integration. For example, if the user is interested in performing an integration between gene expression and copy number variations, and the multi-omics integration, where you can provide all the omics and the package will automatically detect the omics that you provided and perform all the possible integrations. So this is a typical workflow, our workflow for the multi-omics integration in a situation in which the user provided all the available omics. So we start with the so-called genomic integration. So we have the gene expression as response variable, and then we have two covariates, one for copy number variations and one for methylation. We run a single model for each gene. So for each gene, we will have the estimation of two parameters. One is telling us whether copy number variation is significantly affecting gene expression, and another one for methylation. Then we take the residuals of these models, and we that are now representing the gene expression values where the effect of genomic alteration has been filtered out, and we use them for the transcription analysis with transcription factors and microRNA. So this is a screenshot of our Shiny app for the visualization. As you can see on the menu on the left, we have 4 different sections. The first one is the genomic integration for the results regarding copy number variations and methylation. The second one is the transcriptional integration section for results regarding TF, transcription factors, and microRNA. Then we have a class comparison section. In fact, we give the user the possibility to divide the samples in groups. And in this case, we first of all, we perform a complete analysis with all the samples together. And we allow the user to see the results just for the genes that are differentially expressed among the different classes. And finally, in this section, we provide also the possibility to detect the genes that are differentially altered in terms of copy number relations or methylation. And the last section is the complete integration section, where the user can find a circus plot, where you can plot all the omics layer together, all the omics together, and then a data table with the results regarding all the models that have been run. So this is just a case study to give you an example. All the plots that we are going to see are available in the Shiny app. And this is the TCGA cohort for ovarian cancer. As you can see, these are the results regarding the copy number variations integration. And we found that almost 90% of genes have a significant correlation between the copy number variations and the gene expression. And the most interesting thing is that almost every parameter that is significant is actually positive. That is very important because it's what we expect from the biological point of view, because it means that if copy number variations goes higher, also gene expression goes higher, and vice versa. And this is, let's say, an indication of the robustness of the model. And for methylation, for example, we have quite the opposite. So again, we found a lot of significant coefficient, but most of the significant one in this case are negative. And again, this is what you would expect from the biological point of view, because it means that when methylation goes higher, gene expression goes decrease. So again, these are other two plots taken from the Shiny app, just to let you see that the user can see for single genes the correlation between the gene expression and copy number variations in the upper plot, and methylation, for example, in the lower plot. Here we have for PGM3 gene, we can see clearly this positive correlation between gene expression and copy number. Instead, for DP-EP3, we see the negative correlation between the gene expression and the methylation. The last plot that I want to show you is the circus plot in the complete integration section. Well, this kind of plot is really interesting because it allows to visualize different omics together. This circus here is generated with the Gosling R package, and so it is completely interactive. You can zoom in, zoom out, and navigate into the circus plot, and you can also linearize the plot. For example, here we have a zoom in 3 different genomic regions that are highlighted here, and you can see clearly that it's easy to compare the different layers and to navigate into the different genomic regions. So just to sum up, we show how gene omics can efficiently detect the impact of both genomic and transcription alterations on gene expression. Then another strong point is our Shiny app that makes the results interpretation easier and allows also a dynamic, let's say, allows the user to dynamically dive into the results of the different models that we run. And finally, another interesting point is the class comparison section that in fact allows the user to highlight the results only for genes that are differentially expressed among different classes, and also to detect the genes that are differentially altered in terms of copy number variations and methylation. Talking about the future perspectives, we plan to extend these models also to single cell and spatial transcriptomics data, and to analyze ovarian cancer samples in order also to understand how different tumors, the alteration of different tumoral subpopulation impact the immune crosstalks and the metastasis development in ovarian cancer. So I think that's all. I'd like to thank all my collaborators and also you for your attention, your questions. Thank you.
Thank you. Time for questions? I have a question for you. So especially if you're combining multi-omic data sets, the size of them are going to be getting larger and larger and larger. So do you have any tricks on the back end to help if you were to stick in your 1 million heart cells plus other stuff.
Yeah, that's a major problem for bulk data. That is what we support at the moment. We allow the user to parallelize the computation of the different models. So when you run the function that performs the integration, you can specify there is an argument to set the number of cores that you are going to use. And I know that for single site it would be a big challenge to let's say parallelize all the computation to when the number of cells, in particular when the number of cells is really high. But
anybody else? Okay, well, thank you.
So bear with me for 9 minutes, 10 seconds. And then you get your wine, or maybe 17 seconds. Okay, so a small disclaimer before I go into the talk. So this work was initially done by colleagues and collaborators. I'm kind of presenting on behalf of them, but I'm also using this all infrastructure to integrate Shiny apps from single cell data for my own research. So it all started a year ago in spring 2024 when Charlotte, Federico, and Hans visited Freiburg, brainstorming how to host on Shiny applications on Galaxy. So the aims being easy development, and so that the Shiny app developers can leverage the scalable computing infrastructure behind Galaxy. And once it's deployed, we have the flourishing Galaxy community that can take care of maintenance usually. It's actually win-win for both the Shiny app developers and also for the Galaxy user community at the end. And after a few months, I think, or maybe a few weeks or months, they came up with so-called Bioconductor R Shiny container, which follows some best practices to build our Shiny application, as also how to build a container for these Shiny applications. It's built on top of the Bioconductor Docker image. It has a standard way to start. It uses, you have to define standard input and output directories, so you cannot write anywhere on the Docker container. It also has really a tiny feature, but it's actually super useful, like stopping a container, which usually missing, so you can actually have a stop, a close button on your Shiny app, which actually properly shut down the container and close the Shiny app. And optionally, we can also have put and get functions you can for real-time interaction between Galaxy and on your Shiny app, but this is optional. But and the beauty of this container is it can be used independent of Galaxy. It doesn't need to be Galaxy. You can build this with all best practices. You can go out and then run with Docker run, and you're good to go. If you don't know where to start, Charlotte already created a nice template for making your Shiny app into R package so that it can be available for Dockerizing. And Hans made a template for how to create a Docker container. So you can use these two templates, and probably within a day you can have your Shiny app in Galaxy ready. The deployment is similar to as I wrote here. Interactive tools, I probably have to skip this because you've seen this a lot of times, but I just give a quick glimpse. So on Galaxy tools are a bit rigid. You have inputs and output, which are predefined. The ITs, the interactive tools, on the other hand, have dynamic outputs. One example I've seen is RStudio, where you can just install, maybe sometimes also Galaxy allows you to install libraries of our packages of your interest. You can try out some new package and send the results back to Galaxy. And our Shiny application also falls into the category of interactive tools. So once you make this container with the best practices, what you do is you actually define this as a you can actually write a Galaxy wrapper. This wrapper is similar to a normal tool wrapper that you write for Galaxy tools. The only difference is the tool type here is an interactive tool, and you actually define some entry points and commands. So you define your port, also As for best practices, you saw you have to define Shiny input and output directories. So you export these variables, which can be usually set up in the container already, and you run you start your app. And optionally, unless you are not going to do in your local machine, usually this is set up by the system, the Galaxy administrator, to enable the interactive tools. Once you have it, once you deploy it on Galaxy, you see a Shiny app is not, yeah, it's more or less similar to any other tool on Galaxy. You see it on tool panel, and search for it, and then you select your data sets, tweak parameters, and then run the tool. Once you run it, it opens up your Shiny app. So this is not true. Actually, it opens up in a different tab or window, but I'm just for the visualization purpose, I'm showing it here. Probably, I think maybe in the few releases, we will have this as inside the Galaxy. So it's a futuristic view, you can say. And then you have your Shiny app. You can do whatever the Shiny app you're used to do. And you have a close button, you close the Shiny app, and then it sends all the directories which are defined here in the Shiny output directory directly to your Galaxy history. And the apps can also be used within the workflows, in some complex workflows, usually as a final step of your analysis where there's user interaction required. So this is an example of, I don't know whether you can see it, a PhyloSeq interactive tool, which is used to filter and visualize amplicon data. So you can have a complex workflow here at the beginning. So this is not a single tool. If you see, it's a workflow, a whole workflow. A workflow here, which generates any kind of OTU tables. The only prerequisite is to convert this into a PhyloSeq object. Then you're ready to run. Once the workflow is finished, the PhyloSeq IT or Shiny app opens up, and then you can generate plots. I don't know whether you can see it. So you have here buttons to download to Galaxy, which actually puts everything, all the plots that you generate into output directory, which in the end, once you close the Shiny app, as I said, it will transfer all the data into a history. You can also do a real-time interaction with Galaxy. So as I said, if you implement put and get functions, so in R, it's called GX put, GX get, you can actually directly save. So these two buttons, you can actually check it out and save to Galaxy, can on real time sends the plot directly into Galaxy history, so that you can actually, without closing the Shiny app, you can go to Galaxy, generate some reports, or use the outputs of the Shiny app as an input to some other tool you can try out and come back to Shiny app and then reiterate and produce different or analyze differently from your Shiny app. So this gives you more flexibility, so you can actually real time analyze and go back and forth between Galaxy and app. So if you're interested for more discussion, please drop by at post 21. And if you have a Shiny app or if you want to contribute to at the CoFest, we have a project called R Shiny Packaging Galaxy, something around this title. So drop by. I have some nice things to fix, or upgrade some Shiny apps, or even you can bring your Shiny app to develop along with me. With that, I thank all the funding and collaboration partners and also you for your attention. I think that was